Good morning, everybody, and welcome to this last lecture of our course on the latest frontiers of network-on-chip application. And I gave a very direct and exact title to this talk. The brain is richly connected. What about our design and manufacturing technology? This is a challenging question. In the last lectures, we have covered topology analysis in the context of advanced integration technologies such as 3D stacking or 2.5D integration. We have also covered the opportunities for NoC to drive system innovation in fog computing. Today, we are going to review neuromorphic computing and its challenging connectivity issues. Unfortunately, it will not be possible to cover emerging interconnect technologies, the last topic of this course, due to the shortening of this online course with respect to the originally planned one. However, if you want me to give you some pointers, just send me an email and I'll be happy to do that. Okay, let's start. In our daily activities, we typically perform complex tasks, especially related to cognition. And we do that with extreme ease. For instance, we effortlessly recognize objects from among tens of thousands of possibilities, and we do so within a fraction of a second, in spite of tremendous variation in the appearance of each one. Neuroscience indicates we should not take these extraordinary capabilities for granted, because the remarkable capabilities of the brain remain largely unexplored. At the same time, computer scientists are marveled at the computation efficiency in the brain, which can simultaneously handle recognition, reasoning, control, and movement with a power budget of nearly 20 watts. By contrast, a standard computer performing only recognition among 1,000 different kinds of objects expends roughly 250 watts, a big gap. Although this, the brain remains vastly unexplored, its remarkable capability may be attributed to three fundamental observations from neuroscience. They are vast connectivity, a hierarchical organization, which is both structural and functional, and time-dependent neuronal and synaptic functionality. As you can see from this picture, neurons are the computational primitive elements of the brain that exchange or transfer information through discrete action potentials, also called spikes. And synapses are the storage elements underlying memory and learning. The human brain has a network of billions of neurons interconnected through trillions of synapses. Spike-based temporal processing allows sparse and efficient information transfer in the brain. Studies have revealed that the visual system of primates is organized as a hierarchical cascade of interconnected areas that gradually transform the representation of an object into a robust format, facilitating perceptive abilities. Here you can find some references if you want to go into more details. Inspired by the brain's hierarchical structure and neurosynaptic framework, state-of-the-art artificial intelligence is by and large implemented using artificial deep neural networks. In fact, modern deep learning networks are essentially artifacts of hierarchy built by composing several layers of transformations that represent different features in the input. In a deep convolutional neural network performing object detection, like in this case on acquired video, synaptic storage and neuronal nonlinearity are used to learn broad representations about the data. After training, the features learned at each layer show interesting patterns. The first layer here, learns general features such as edges and color blobs. As we go deeper into the network, the learned features become more specific representing object parts to full objects, such as the face of a person. Such generic to specific transition is representative of the hierarchical arrangement of the visual cortex. With the development of neural networks, computers today have demonstrated extraordinary abilities in several cognition tasks. For example, the ability of the AlphaGo computer program from DeepMind Technologies to defeat human players at the strategic board game Go. Again, the starting point of this lecture is very far away from networks on chip, and we will land onto networks on chip later, because we need to understand the concept where we are going to design our networks. Such neural networks are fueled by hardware computing systems that fundamentally rely on basic silicon transistors. Digital logic in massive computing platforms today comprises billions of transistors integrated on a single silicon die. Reminiscent of the hierarchical organization of the brain, various silicon-based computational aspects are arranged in a hierarchical fashion, as you can see here on the left-hand side. And this is to allow efficient data exchange and computation. Broadly, the computing hierarchy is divided into processing units and memory storage. The physical separation of the processing unit and the memory hierarchy results in the well-known memory wall bottleneck, as it is represented here. In spite of this bottleneck, silicon computing platforms such as CPUs and GPUs have been enabling factors in the current deep learning revolution. In fact, in an artificial neural network, most operations can be represented as matrix vector multiplications. Therefore, they can be performed conveniently with conventional computing platforms such as CPUs and GPUs. Even better if assisted by some coprocessors specialized for this kind of computations. Today, deep neural networks are trained on powerful cloud servers, yielding incredible accuracy, although incurring, and that's a problem, huge amounts of energy, hundreds of thousands of watts on cloud servers. This is exactly the problem that we are facing. What is the computing cost involved with deep neural network computations? And this is the computing cost that brings us such impressive performance, but that's a huge amount of overhead. This question does not only come to the forefront when we compare the 20-watt power of Lee Zeldon's brain with that of data center machines when playing the Go game. Think about another computing domain, the edge computing domain. It has been recently demonstrated that running a deep neural network on an embedded smart glass processor supported by a typical 2 watt per hour battery would drain the battery completely within just 25 minutes. Overall, the point is that the brain seems to have something very special about energy efficiency that we are trying to reproduce. Well, if we look more carefully, we can immediately observe that deep neural networks running on top of silicon computing platforms have some biological inspiration only, but are still quite different from the brain, both in the learning methodology and in the computing concept. There exists, in fact, a sharp contrast between the computing principle of the brain and those of silicon-based computers, as we can see in this list. First, the segregation of computations, the processing unit, and storage, the memory unit in computer, contrasts with the co-located computing and storage mechanisms found in the brain. Neurons, the computing units, and storage, the synapses, are co-located in the brain. Second, the massive three-dimensional connectivity in the brain is currently beyond the reach of silicon technology, which is limited by two-dimensional connections and finite number of interconnected metal layers and routing protocols. Third, transistors are largely used as switches to construct deterministic Boolean circuits, Boolean logic. In contrast to the spike-based event-driven computations that take place in the brain and that are inherently stochastic. Just to mention a complementary aspect to the computing environment, it's worth mentioning that applying, I think you know about this, applying imperceptible, non-random perturbations to a test image, it's possible to arbitrarily change the network prediction. And this is called adversarial example. With just a minor modification of the pixels of a street sign, you can fool the neural network that can interpret it as, for instance, an animal. Human learning, what this tells us is that human learning is definitively more intelligent than deep neural network learning. But this is a complementary story, and I don't want to further consider that in this presentation. The focus of this presentation is clearly on the computing platform. Overall, we can now understand the dream of neuromorphic engineers, beginning from the pioneering work of Carver Med in 1989. And the dream is to design systems that work even more like the brain, that is neuromorphic hardware. And this is done in order to grasp and capitalize on the secrets of the energy efficiency of the brain. In the 1980s, almost 4 decades after the invention of the transistor, Carver Med envisioned smarter and more efficient silicon computer fabrics. And he was envisioning this based on certain aspects of biological neural systems. Instead of focusing on Boolean computing based on logic gates, Med focused on analog distributed computing circuits that mimicked neurons and synapses. Interestingly, he suggested that his initial attempts to build such neuromorphic systems were simple and stupid. That's his definition. Nonetheless, his work represents really a new paradigm in hardware computing and the beginning of a new research field, neuromorphic computing. Spiking neural networks are different from artificial neural networks, and they are a step forward toward mimicking more closely the computing concepts of the brain. In a spiking neural network, computations are triggered by events. That is, computations take place only when spikes, when voltage pulses occur. Such an event-driven computational model has the advantage of being energy efficient, if you think about it, because spikes in a neural network, as you can see in this picture, are typically sparse, both in time and in space. This is a key concept. And if you think about it, it is exactly the high power demand for inference of artificial neural networks which is limiting their spread in contexts where energy matters a lot, such as devices at the infrastructure edge. At the same time, spiky neural networks demand specialized hardware that can match this event-triggered computational model. The picture shows an example comparison between the output of an artificial neural network and the output from a spiky neural network. For the artificial neural network, the output of the network consists of the probabilities associated with predicted labels. It's not a function of time, as you can see. It's fixed for a given input. And therefore, inference can be made after the entire forward pass is completed. For the spiky neural network, the output is a spatial temporal pattern. They are trains of neurons' output spikes. Therefore, one can make inferences at any time based on the current available information. For instance, we could train the spiky neural network model with the objective that when a specific input is presented to the network, say a specific digit in a digit recognition application, one output neuron fires with a high firing density, while all other neurons fire at a lower density. That's a fundamental difference. From the above description of information processing as spike-based communication, a few characteristics of our systems that aim to form the underlying compute base for spiky neural networks can easily be hypothesized. Among these, we find the following items. First, the sparse event-driven nature of the underlying hardware. We require a sparse, event-driven nature of even the underlying hardware as a direct manifestation of the spike-based information exchange. So the hardware needs to match the computational and communication model. Second, the requirement for tightly intertwined computing and memory fabrics, inspired by the ubiquitous presence of neurons and synapses throughout the biological brain. Computing and memory are co-located in the brain. Last but not least, the need to implement complex dynamical functions. For example, neuronal and synaptic dynamics using minimal circuit primitives. So what these circuits need to do is to learn with the spikes. I will, of course, not dig too much into this in this presentation. So learning with spikes is outside of the scope of this presentation. But intuitively, this implies a lot of dynamics in the underlying platform, and this needs to be reflected in hardware. These requirements have shaped the evolution of neuromorphic hardware since the early intuition to the current days. As already anticipated, Carver-Mead in the 80s exploited the inherent device physics of the MOS transistor in the subthreshold regime, where current and voltage characteristics are exponential, to mimic the exponential neuronal dynamics. This device circuit co-design approach remains mainstream to the advent of throughput computing via GPUs. They were providing enough computation capacity to become the reference platform, not only for running deep neural networks, but also for exploring inference and training for spiky neural networks. While GPUs to provide an obvious advantage for their increased programming flexibility, they do not explicitly leverage, and that's an issue, they don't explicitly leverage the event-driven nature of spiking computations. Therefore, as time went on, the unmistakable trend was to encompass the event-driven nature of spiky neural network computations. In the early 2000s, such research efforts facilitated the emergence of large-scale neuromorphic chips, such as Pinnacle from University of Manchester, IBM's True North, or Intel's Loihi that we will review in this presentation. These so-called big brains chips are distinguished by integrating millions of neurons and synapses that render spike-based computation. Since recently, however, device circuit co-design is again on the rise, and currently one of the most fascinating areas in neuromorphic computing, driven by novel emerging materials and associated devices such as resistive RAMs, phase change memories, and optics. These devices, these emerging technologies exhibit similar behavior to what happens in biological synapses and neurons, and this potentially leads to ultra-low power neuromorphic circuits, although the potential still has to be fully exploited. Many of the computations in neuromorphic hardware lend themselves to the sort of operations that analog systems naturally perform. And that's why analog realizations are so popular in this domain. If you think about it, the biological brain is an analog system and relies on physical properties for computation and not on Boolean logic. Analog systems represent the membrane potential of a neuron as a charge stored on a capacitor. Neuronal dynamics are implemented then through current sources feeding into a sinking through the capacitor. That simple mechanism. It has been pointed out that custom analog integrated circuits and neuromorphic systems have several characteristics that make them well suited for one another. Unfortunately, analog systems tend to be significantly more noisy than digital systems. However, there have been some arguments that because neural networks can be robust, inherently robust, from the ground up to noise and faults, they may be ideal candidates for analog implementation. So you can tolerate the drawbacks and you can exploit the advantages of analog realization, such as typically asynchronous operation, dealing with continuous values, built-in support for important operations such as conservation of charge, amplification, thresholding, integrations, and so on. In addition to fully analog realizations, Another important class of neuromorphic hardware falls into the category of mixed analog digital systems that are very common as well. In fact, there are, as I was mentioning, several issues with analog systems that can be overcome only by using digital components. I mentioned reliability. It's the current source of debate whether this actually plays in favor of analog realizations or this actually calls for more and more digital circuits. And this, however, justifies the use of digital circuits for neuromorphic hardware, especially digital storage, while keeping the computation circuitry analog, or digital communication. Then Stanford Neurogrid Big Brain chip is an example of a mixed signal analog realization. It hosts more than 65,000 neurons and 500 million synapses. And its network on chip realizes, as you can see in this picture, a tree topology. Neurogrid was designed to assist computational neuroscience in emulating brain activity. Another example of analog digital mixed signal realization is the Heidelberg Brain Scale S project. Other realizations use all digital technology, as you can imagine. In general, digital neuromorphic systems such as the IBM True North, illustrated here, represent the main brain potential of a neuron as an n-bit binary word. And this binary word is simply kept updated by local learning circuits that follow predefined adaptation rules, learning rules. True North, one of the most popular present-day neuromorphic implementations, is a full custom ASIC design. It comes with 1 million neurons and 256 million synapses and relies on a network on chip that follows a 2D mesh topology, as you can see in the picture. True North originated as a neuromorphic chip geared towards solving commercially important tasks such as recognition and classification using Spiky neural networks, and is based on simplified neural and synaptic primitives. Another big brain chip that falls into the category of fully digital realizations is the Spinnaker neuromorphic system from University of Manchester. Last but not least, emerging technologies. To keep pace with soaring demand for computing power, researchers have recently begun exploring a twofold approach to enable both beyond von Neumann and beyond silicon computing models. Along this track, non-standard device level or circuit level components are being increasingly considered for neuromorphic systems. They mainly include a variety of components that have traditionally been used as memory technologies, mainly memristors. Here, the size of the boxes represent the amount of works in the open literature that use a specific technology. So memristors are by far the dominating emerging technology for neuromorphic systems. As an example, the most common use of a memristor in a neuromorphic system is to build a memristor crossbar to represent the synapses in the network. These are memristors, and this is a memristor crossbar, and they represent a synaptic network. These kind of crossbars exhibit, and especially the constituting building blocks, memristors, exhibit two of the most important characteristics of biological systems, synaptic efficacy and synaptic plasticity. The plasticity is the ability to modulate the weights of the synapses based on a particular learning rule. The synaptic efficacy refers to the phenomenon of generating an output based on an incoming spike. In its simplest form, this means that incoming spikes are multiplied by the stored weights. So here we have on the left-hand side incoming spikes. They are multiplied by the stored weights of synapses. As you can see from the picture, this is typically implemented as a programmable, analog, and non-volatile resistance value. The way it works is the following. So you get a spike from the left-hand side, and this results in a current, and this current is proportional to the conductance of the memristive element in accordance with the Ohm's law. The currents through the multiple spiking preneurons are summed along vertical lines, and this is a consequence of the Kirchhoff's current law. So all the currents are summed along the vertical lines. This results in the in-memory dot product operation that represent synaptic efficacy. Synaptic plasticity is generally implemented in situ and locally by appropriately applying a voltage pulse whenever the pre and post neuron spike on the horizontal and vertical line. And this is in accordance with a specific learning rule. So you can see here these pre-neuron spike and post-neuron spikes that all together yield the plasticity of the weights of the crossbar array. The resistance values of the constituent memristors are therefore programmed on the basis of the resulting voltage difference across the respective horizontal and vertical lines. Additionally, the figure shows that such crossbars are typically connected hierarchically through a network on chip to build dense, large-scale neuromorphic processors featuring in situ in-memory computations. Last but not least, optics. In the early days of neuromorphic computing, optical implementations were very popular, but it was soon noted that it was difficult to implement optical storage. Therefore, they lost relevance for a while. In more recent years, optical implementations and photonic platforms are again on the rise because of their potential for ultra-fast operation, for sure. Optical neuromorphic implementations today include optical synapses, including using novel materials, and optical neurons as well. Regardless of the specific implementation, there are a couple of common features to most recent neuromorphic processor realizations. Let us take a look at them to familiarize deeper with the field. The first one is the asynchronous nature of spiky neural network. That's a fundamental issue. Spiky neural network-based neuromorphic systems closely follow biological inspiration, and they achieve energy efficiency by exploiting asynchronous event-driven computations. No explicit synchronization assumption is implied. There is no explicit synchronization in the brain. It's fully event-driven asynchronous operation. As a result, neuromorphic hardware exhibits a high degree of sparseness in both time and space. And for this reason, the matching compute base for such sparseness of the computational model in time and space is asynchronous design. Asynchronous realizations of neuromorphic processors, they allow event-driven onset of circuit activity. And this indirectly means that no additional power other than leakage power is consumed during idle periods. In other words, we get rid of the traditional idle power, which is associated with the clock running, regardless of the circuit activity. Even though you have no activity, the clock is running. It's true that you have clock gating techniques nowadays in VLSI circuits. However, they are not so efficient at minimizing this idle power. Asynchronous designs are more efficient in burning no power when there is no activity. Another advantage of asynchronous design is that each module in the design can converge to its differentiated local operating speed. In other words, there is no need for performance equalization, both within individual pipelines and across different pipelines in the design. Every pipeline stage can naturally operate at its natural operating speed, and the coordination with each other takes place through clockless handshading. Last but not least, backend timing closure gets simplified with asynchronous design, since all timing constraints apply only to neighboring, physically proximate asynchronous pipeline stages. And this leads to a locally optimized, fully distributed design. Moreover, system-level design is also facilitated, since you just have to put the components together at the system level during the system-level composition phase, and these components self-regulate their interaction through a local asynchronous and shaking protocol. You have no such thing as controlling the skew of the jitter of your clock tree, which leads to power-hungry clock power instantiation. And design convergence is way easier due to a fundamental focus on the individual system components and due to the hopefully correct by construction assembly of such components at the system level. You put the things together and they should work. There is an implication of this asynchronous design for neuromorphic systems. And these characteristics that I'm going to present now is common to both analog and digital systems. They use the address event representation for spikes. The address event protocol is nothing else but an asynchronous handshaking protocol. And this is used to transmit signals between any two neuromorphic systems. And it's very important because networks on chip in this domain, they carry address event representation traffic. Address event representation emulates massive connectivity between cells, but it emulates that. So you have cells on the left, you have cells on the right, and this protocol emulates massive connectivity, one-to-one connectivity between cells on the left and cells on the right. And it does that by time multiplexing many connections on the same data bus. The mechanism of AER representation is shown in this picture. And you have incoming pulses here on the left-hand side from each channel, from different channels, for instance, from different neurons, that are encoded by an encoder. And the encoder associates the address of the source to this spike. So this spike is changed into the address of the source. So in general, in this representation, computational units, the neurons, are assigned an address, and this address is encoded as a digital word and transmitted as soon as these neurons produce an event. They produce a spike, and this is done using fully asynchronous digital circuits. The asynchronous nature of AER circuits, that's very important, neglects the need to send timing messages along with pulses. We don't send timing messages along with pulses. Time represents itself as the asynchronous occurrence of the event. So the AER protocol is nothing else but event-driven communication. And this is a fundamental way of triggering computations only when a spike is generated. Previous work has shown that AER can also be used to construct large-scale networks with arbitrary, configurable synaptic connectivity. This is key to have neuromorphic systems that are flexible, that can accommodate arbitrary network topologies. But in this case, we end up having multiple AER endpoints, not just point-to-point communications as it used to be in the early days. And this implies some additional overhead, and we will come back to this later. That's very important. The first one is a mapping overhead from source neuron addresses to destination neuron addresses, because you need to program the synaptic connectivity. You need to set up the connectivity between a source neuron that generates spikes and the destination neuron that consumes them. And we will see that this kind of programming, this kind of mapping, requires large memories to support reconfigurability, and that's an issue today. That's a special issue today. The second source of intricacy is that we need, like in a system like this, think that here we have neurocores. In a system like this, you need the routing architecture from one neurocore to the other. You have to find the packet way to destination. Last lecture was mostly about this. This is typically overlooked in this domain, but this means that in the end, you may have additional memory resources to implement routing tables. Last but not least, the network on chip. We started far away, but here we are. The network on chip became relevant in this domain when the community moved from small-scale realizations of neuromorphic systems to large big brain chips. Because networks on chip are still considered the ideal solution for scaling up system size in a modular way. It has to be pointed out that networks on chip are only a not even close approximation of brain connectivity. Because as you can see here on the right-hand side, the brain has a complex 3D structure. And each neuron, on average, projects to roughly 10,000 destinations. That's an impressive fan-out. In contrast, connectivity in a typical silicon fabrication process is largely bidimensional, with limited flexibility in the third dimension. NoCs are still the best way to connect lots of architectural units in 2 dimensions. In 2010, a theoretical analysis from Technion demonstrated that the 2D mesh is still the preferred topology for configurable emulation of spiky neural networks over fat trees, point-to-point architectures, and shared buses. There are recent works that question this analysis, and they actually see a trade-off between these solutions. But as a matter of fact, most large-scale systems use a 2D mesh topology, or torus in the best case. So in this domain, the key differentiating feature of the NoC is not the topology, but its synchronization paradigm. Ideally, we want an asynchronous event-driven communication architecture, carrying address events and using clockless handshaking instead of clock-based synchronization. So the fundamental characteristic is that here we're going to use asynchronous interconnection networks. Finally, we know that despite the use of networks on chip connectivity still cannot rival the 3-dimensional connectivity found in the brain. By recent advances in system integration, we are moving a step forward in that direction, but we're still far away. Think about the fan-out that you have in the brain. On the other hand, regular networks on chip, they enable arbitrary node-to-node communication. It's not a hardwired huge fan-out connection, but it allows arbitrary node-to-node communication in the system. Every node can talk to every other node by means of a regular topology that has limited connectivity. This is a very important concept, and next slides will be about that. Given a regular connectivity pattern, you can think of freely mapping any spiky neural network topology on top of this. You can take an arbitrary spiky neural network topology and map it onto a NoC-based system. You can accommodate the neurons in the different neurocores, and all the communications can go through the on-chip network, since any node has a routing path to any destination node. However, as we will see in the slides that will follow, the mismatch that we have between the possibly huge number of logical SNN connections, the huge number of logical spiky neural network connections and the available physical connection, there is a mismatch, there is a clear mismatch here. This mismatch is sooner or later going to come up. The mismatch between these two domains on the right-hand side is going to come up very soon and to bring important limitations on the kind and size of spiky neural networks that can be mapped onto nowadays neuromorphic chips. This is a fundamental issue. That's why in this slide we try to touch more directly where the problem is, the implications of the fundamental mismatch of our computing and communication technology and the structure of the brain. What I'm going to present now is an oversimplified scenario, but gives the idea of the problem in a very clear way, regardless of the specific optimization of the different implementations. You can find the details in this paper here. Consider a generic spiky neural network with n neurons. So we have n neurons, and the neurons have this structure. They have inputs, so they have these synapses that establish the connectivity between this neuron and the previous neurons, and you have a specific fan out, and this closely reproduces the structure of the brain, where we have neurons, then we have axons that are used for the communication between this neuron, this subbody, and a number of axon terminals. Okay, so a number of destinations can be reached through these axon terminals. And so similarly, let us assume that we have a spiky neural network with n neurons, in which each neuron has a fan out of f. So each neuron is spikes to other f neurons. This is the case for many neural network models, including possible models of cortical networks, including recurrent neural networks, convolutional networks, and deep networks. So in the standard address event representation, each neuron would be assigned a unique address encoded with, in this case, the base 2 logarithm of n. N is the number of neurons, so to encode the address of each neuron, you need the base 2 logarithm of n. These are bits, these are memory resources. Therefore, to support a fan out of f destinations per neuron, a storage of f base 2 logarithm of n bits per neuron would be required. In total, the size of the connection memory for the whole network would be n times f times the base 2 logarithm of n. So this is very expensive, if you think about it. This is extremely expensive. So while this scheme and the use of this connectivity table can support any type of connectivity, it is very wasteful in case of spiky neural networks that have only specific structures, partial connectivity. And this holds for most of the real and artificial neural networks. So the point here is that we need connectivity tables to program the connectivity of our target spiky neural network into the system. And it takes quite a lot of memory. Overall, this is an important statement. Today, the scalability of neuromorphic systems is mainly restricted by connectivity requirements. Connectivity in this domain doesn't mean only network on chip requirements, but it is a broader notion of connectivity. It requires the connectivity programming support in the platform. Due to the overhead of keeping the connectivity state for programmable fan-outs, it becomes an enormous challenge to support networks with high connectivity using today's integrated circuit technology. Let's see in a real case study where and when the problem arises. Because I have presented the problem in general terms, but now let's see when designing an actual neuromorphic system where the problem and when the problem exactly arises. In this slide, I will present a real case study, the Intel Lohis chip. It is the 5th generation of self-learning neuromorphic test chips for research purposes. It was introduced in November 2017 by Intel Microarchitecture Research Lab. It comes right after the previous densest Spiky neural network chip, which was the IBM True North chip. And this is even denser in terms of the synaptic variables per square millimeter. With respect to the True North, the density of Lohi in terms of synaptic variables per square millimeter is 3 times larger. But the neuron density, on the other hand, is 2 times smaller with respect to True North, and is due probably to the extended support for the feature set of the Lohi chip. So it supports a wide number of learning capabilities and configuration options. So this design is fabricated on Intel's 14 nanometer process, and the Lohi chip is a mini core processor that consists of 128 neuromorphic cores, and each core can implement several neurons. So let's say a cluster of neurons are implemented, are mapped to a neuromorphic core, and this adds up to a total of some 130,000 neurons, each of which can communicate with thousands of other neurons. Interestingly, this Spiky neural network implementation has on-chip learning capability. I will not go into the details of how we can learn with spikes and how to implement that. This is outside the scope of this presentation. But for your information, this results into a local learning engine, which is embedded in each one of the 128 neurocores. To demonstrate the superiority of Lohi in solving large-scale parallelizable problems, an L1 minimization problem called Lasso was benchmarked. Compared to a baseline CPU running a numerical solver with the same operating voltage and manufactured on the same process node, Lohi was able to achieve more than 5,000, actually I think 5,700 x, so more than 5,000 x in the energy delay product when the size of the problem was large. Okay, you can exploit the benefits of this chip when the size of the problem is large. Recently, a programming toolchain has been introduced to allow running more variable spiky neural network inference and training applications on top of this architecture. Lohi 128 neurocores are structured in a 2D mesh grid. And this is done using a network on chip with the same topology, the 2D mesh. Each neuromorphic core implements 1,024 primitive spiking neural units. So neural units that have spiking capability. They can be also connected together to form higher order spiking structures. Interestingly, Lohi implements 2 instances of an asynchronous network on chip. And so it has 2 networks on chip actually. And they are used to solve protocol-dependent deadlock problems. A protocol-dependent deadlock is a problem that arises when in a system you have messages of different type, For instance, you have memory requests and memory responses, and if you accommodate both of them onto the same network on chip, you may close cycle through the cores. So you may end up in a deadlock condition, similar to the routing deadlock of the network on chip itself. So in order to avoid these blocking conditions, typically you need to associate either a virtual channel or a separate network on chip to each different message class. And this is what is done here. But from the viewpoint of the spikes, spikes are unidirectional messages. These spikes in the form of address events, they are alternatively injected to one versus the other network on chip by each core for efficient bandwidth exploitation. So each core sends one spike to one network on chip, another spike to another network on chip in an alternating way. So this is tricky. This is possible because this is not a very elegant thing, because you may end up into troubles, you may end up into out-of-order delivery. But this is possible only because with this computational model, the spiky neural network, this computational model does not depend on the spike sequence ordering within a time step. So within a time step of the SNN algorithm, the computation does not depend on the spike sequence ordering. And that's why this alternated injection into the different NoCs is feasible. Let's see now the operation of the neuromorphic mesh as it executes a spiky neural network model. And to understand that, we need to recall that although real networks exhibit continuous time dynamics, this is the characteristics of real networks, of real SNN networks, Lohi approximates this continuous time dynamics using a fixed size discrete time step model. So it uses a discrete time step model. This way, all neurons maintain a consistent understanding of time so that their distributed dynamics can evolve in a well-defined synchronized way. This has to do with the algorithm. This is an algorithmic issue. This is splitting into a discrete time step model. This has nothing to do with the underlying hardware, which is clockless and fully asynchronous. This is an algorithmic issue. At each algorithmic time step, the state variables of the spiking units are updated in a time multiplexed pipelining manner. So in a neural core, you have a number of neurons that are executed, but their state is updated, and the state of the synaptic links is updated in a time division multiplexed fashion, in a pipelined fashion. The reason for this, this is very common in neuromorphic systems, is that these kind of systems need to keep up with biological systems, with the biological dynamics. And these biological dynamics are in the order of milliseconds, and silicon is typically too fast for that. So we need to capitalize on the higher speed of silicon, for instance, to multiplex the update of the spiking unit in time in each neural core. This is pretty common in this kind of systems. The way it works is that when you evaluate a spiking unit, when the membrane potential exceeds a threshold level, it generates a spike message that is routed to a set of fan-out neurons. And these fan-out neurons will be in destination neural cores. So now assume that all cores begin at algorithmic time step t. Each core independently iterates over its sets of spiking primitives, and any neurons that enter a firing state generate spike messages that the NoC distributes to all cores that contain their synaptic fan-outs. Spike distributions for two such example neurons, N1 and N2 in core A and B, are illustrated in this animation. So the spiking neuron in neural core A is spiking with a fan-out of 2, while this N2 neuron in core B is spiking to a single destination neuron. Now, as time goes on, additional spiking distributions from other firing neurons add up to the network on chip traffic. You can see, so here we start adding up the traffic from firing neurons throughout the entire platform. The network is distributing these spike messages with address event representation. In this case, according to an X and Y algorithm. So spike messages are routed first along the X direction and then along the Y direction. I guess they are using algorithmic routing in the sense that they have some small hardware routing logic in every router. The network on chip itself only supports unicast distributions. So what happens when we have to spike to more than one neuron? In this case, we need multicast. So there are some solutions that come with multicast directly in hardware, but in this case, it is implemented actually in software. In fact, to multicast packets, to multicast spikes, the output process of each core iterates over a list of destination cores for a firing neurons fan-out distribution and sends one spike per core. So it is actually changed into an iterative transmission process. Finally, the last course of action that is taken in this system is that once each core has finished processing its local neurons and synapses, after processing and updating their state, they need to move to the next epoch. They need to advance to algorithmic type step T+1. So this is done by each individual neuron after all of its spikes have been delivered. And the way the neural cores synchronize with each other to move to the next algorithmic type step T+1 is through the exchange of barrier synchronization mechanisms, and is represented in this picture. The barrier messages that are propagated throughout the network, they carry a time step advanced notification to all cores. Interestingly, the network naturally evolves to the next algorithmic step in a fully distributed way through the use of the asynchronous network on chip, without the use of any global distributed time reference, without the use of a global clock. So asynchronously, in a fully distributed way, but in a coordinated way, the network advances to the next algorithmic time step. Let's see now how a spiky neural network can be mapped to this architecture. This slide shows an example of a simple 7-neuron network mapped to 3 cores. So you can see here that we have this simplistic spiky neural network where one presynaptic neuron spikes to 7 different postsynaptic neurons. And these neurons are actually mapped to 3 different neural cores. So each neural core has the capability to accommodate different neurons. But here we are assuming that we are mapping them to 3 different neural cores. And you can see that the spiky neuron X is placed here, and it has to send spikes to F, E, D in neural core 3, B and C in neural core 2, and to A in neural core 1. Well, bear in mind that every synapse has a state. So each one of these links here with the arrow in black, each synapse has a state, and it is identified with this spiking symbol. And this state in this Lohi realization is, I think, a set of 3 properties that are integer valued. So you have some state for every synapse, and this chip has local autonomous capability to evolve these properties over time. It has on-chip learning capability. But this is done on-chip and autonomously by this chip. So given a particular neuron to core mapping, each neuron synaptic fan-in state, so this synaptic state, must be stored in some memory. And this adds up to the core's synaptic memory. Okay, so the state of the synapses is stored in this synaptic memory. And this is the first memory requirement of the system, the synaptic memory. Sorry, the animation here is screwed up, so let me introduce directly all the animations at once. Second, each neuron fan-out edges, for instance, X has a fan-out of 7, which leads neurocore 1 to have communication with neurocore 3 and 2. So each neuron fan-out edge is projected to a list of core-to-core edges represented here in yellow. No? We need to program the connectivity of this neurocore through 3 other neurocores. And you need a programming table for that. You need memory for that. Each core-to-core edge, each yellow box here, is assigned an axon identifier, which is unique to its destination core. And this closely resembles the biological structure of the brain connectivity, because through this axon, you have a fan-out to a local number of destination neurons. Therefore, you need to associate each core-to-core edge with an axon identifier. So again, you need memory resources here. When a neuron spikes, the axon identifier is routed through the network on chip to the destination core. And here, through an additional memory, this axon identifier that will be carried by the packet is expanded into a list of synapses. And this is the red memory here. This is another piece of memory, indeed, for the synaptic list, for the expansion list, for the distribution list. For each synapse, the state is fetched from the synapse memory and possibly modified. So once you get the axon identifier, you expand this into a synaptic list, and then you can fetch the state of this synapse from the synaptic memory. So this connectivity architecture can in principle support arbitrary multi-graph networks, but we need to take into consideration the resource constraints, the actual resource constraints. In theory, you can do whatever you want, but in practice, you have resource consumption constraints. And let's take a look at them, because this is a fundamental vulnerability for the scalability of neuromorphic chips. So, first thing is that the total number of neurons assigned to any core should not exceed 124. This is not reported here, but the number of neurons that you can accommodate in each neurocore may not exceed 1024, so 1024. The other constraints are essentially memory constraints. In fact, the total synaptic fan-in state mapping to any core, so this synaptic memory here on the right-hand side, must not exceed 128 kilobytes, subject to compression and list alignment considerations. Moreover, the total number of core-to-core fan-out edges here, the yellow boxes, must not exceed 4,096 entries. Okay, so you cannot have more than 4,096 yellow entries here. Similarly, the total number of synaptic list entries, so the red boxes at the input of the neural cores, must not exceed 4096 entries. This is the number of input side axon identifier routing slots. It is highlighted here in red. So clearly, in order to program a spiky neural network on top of this system, you end up having requesting a huge amount of memory resources. And that's the fundamental bottleneck of this architecture, of these architectures. It has to do with the connectivity state. And from the experience of the designers over here, it turns out that the most limiting factors here are the constraints on the right-hand side, the constraint on the synaptic memory and on the synaptic list. These are the constraints that come into play first to limit the design space of mappable spiky neural networks. For your records, we have another solution. This comes from Giacomo Indiveri's group in Zurich. I will not go into the details because we don't have time for that. It's just an alternative realization that by configuring specific, by defining specific connectivity requirements of neurons with all other neurons, by limiting these connection capabilities, and by properly arranging the network on chip in a hierarchical structure, they end up limiting the memory requirements to program the connectivity. So as you can see here, each neuron is not connected to any other neuron. It has a limited fan-out. So this limited fan-out is not accessing the destination neurons directly, but it is accessing intermediate points, intermediate routers. And through these intermediate routers, the spikes can be broadcast to a local cluster of neurons. And at most, M, a subset of these neurons, can be subscribed to this source neuron. So there are limitations in the connectivity and in the subscription capability. And this is because the assumption is that the structure of many spiky neural network is a clustered one, where you have local connectivity among a cluster of neurons, and then the neurons can reach the population at large through few long-range links. And this is exactly reproduced in the feasible connectivity of the platform. And this feasible connectivity is reflected into the network on chip organization. In fact, you have a level 1 network on chip router, which is used to broadcast spikes to the neurons of the local cluster. Then you can have this level 2 router, and there can be actually multiple of them organized in a tree topology that actually deliver the intermediate routing options. So these intermediate blocks here. Overall, this adds up to a neurochip, and you can connect different neurochips together through a level 3 router. And for the level 3 connectivity, you have a mesh topology. Overall, if you do the math, the memory requirement to program connectivity is not f times the base 2 logarithm of n, but it is the square root of this quantity. So it has a much better scalability. So you can see that in any case, the tricks to relieve the connectivity state limitations is to assume some kind of clustering of neurons together. Anyway, I refer you to the papers for further details. Okay, so I think it's time for a break. So let's have, let's say, 10 minutes break. And you can post your questions meanwhile. And right after the break, we can answer the question and move on with the technical content. Thank you and talk to you soon. Hello, let's start again. So I got this nice question that I'm going to try to answer now, although the answer could be very complicated. Well, there are actually, so the question is, how much does the spiky neural network reduce the energy in comparison to the artificial neural network? So there are a number of papers, actually not too many, that try to compare the two approaches on a common experimental setting, on a common background. Yeah, I think that rather than going into the specific assumption of one paper versus the other, I would like to report some data from the working chips. For instance, the IBM True North, it was manufactured in 28 nanometer technology. And the power consumption, this chip was roughly tens of milliwatts. Okay, tens of milliwatts, with the capability of billions of synaptic operations per second. Yeah, I'm aware of power consumption for a complex recurrent neural RRN network on top of this True North chip, and it was reported to consume less than 100 milliwatts. Okay, and the density was 20 milliwatt per square centimeter. So it means that, and I found similar numbers for the NoC chips. In that case, it was specified that for inference, you consume a few milliwatts. For training, the power adds up to tens of milliwatts. Although here we are in a more scaled process node, since it's 14 nanometer as opposed to 28 nanometer. So, but the point is that in general, the current power consumptions are in the order of from few milliwatts for inference to tens of milliwatts for training. So if you compare this with artificial neural networks, then you have to consider the underlying computing platform. And clearly, if you start using GPUs and the like, then the power consumption easily skyrockets in the order of tens of watts, even more. Just for the sake of comparison, I have recently worked with the deep learning accelerator from NVIDIA, which is open source. It's called NVIDIA. And for the NVIDIA accelerator, for a ResNet 50 network, the power consumption is in the order of hundreds of milliwatts in a 16 nanometer technology. So consider that we are talking about a 16 nanometer technology. We are considering inference, and as opposed to let's say a few milliwatts in a 28 nanometer process. So the advantage is actually there, and it can be by orders of magnitude. But the most interesting thing is that similar to what's going on in the accelerator domain, where people are trying to come up with more and more power efficient accelerators for deep neural networks, there is a similar race for neuromorphic chips. But here the targets are much more ambitious, because you are computing much more like the brain. So you have higher opportunities to scale your power figures, and think that the cost in nature for a synaptic operation is roughly 2 femtojoule. And currently, with our silicon implementations of neuromorphic systems, is something like a few picojoules. So the margins for improvements are still orders of magnitude with respect to what the nature is able to do. Okay, let's move on. After reviewing connectivity issues in state-of-the-art neuromorphic systems, let's come to an important consideration, because while I was reviewing all the material, and this started in the past year since the big brain chips started to come out, I had the clear impression that, to use an analogy, we were building a skyscraper, that is the neuromorphic system, without caring too much about the foundations. And the foundation is the asynchronous network on chip. Because the question is the foundation stable? So can we consider the asynchronous network on chip just as a commodity that we can use to build any kind of neuromorphic system? I would say that the foundations in this case are not stable enough. Plainly speaking, we said that we should ideally use this event-driven communication fabric, this asynchronous interconnection network, to allow system-level integration at overly low power. And this also comes with other nice features that I have reviewed in the first part of this presentation. Nice features about asynchronous realizations in terms of exploitation of the sparsity that we have in space and time in spiky neural networks. However, if you look at this thing more closely, let's see, okay, it's working. We can understand that there are some issues also considering that not all neuromorphic chips use clockless networks on chip. Some of them use synchronous NoCs, although this is admittedly not the most efficient implementation. Smarter solutions use multi-synchronous realizations, that is, a network on chip is split into the voltage and frequency domains of neurons or clusters of neurons. So there is a reason why not everybody is using a clockless NoC. And the reason is because it's not very difficult, it's not very easy to design an asynchronous interconnection network. So if I ask you, do you know how to design a synchronous interconnection network? The answer probably would be no. But then let's ask for tools to automatically instantiate an asynchronous NoC in a system, even without being an expert of this kind of asynchronous design thing. But the answer is again not exciting, because there are tools and methodologies that yield very good results for asynchronous NoCs, and that are in some cases even industry grade, but they either do not integrate with mainstream industrial CAD tools, or they do, but they are proprietary since they have been developed within companies. So they are not available for the research community at large. There are actually tool flows that are compatible with the mainstream industrial CAD tools and that have been published, but they are either unoptimized or, in the best case, and we have such best cases, they are not easy to reproduce at all, because they imply some hacking on top of these mainstream industrial CAD tools. So this doesn't sound like an ideal situation to enable design space exploration. And when it comes to the network on chip architecture, yes, there are some consolidated asynchronous architecture, even used for several industry-grade prototypes, test chips. But, and this is an issue that is currently overlooked, they do not really match with the ultra low power, ultra low area requirements of a neuromorphic system. No, we need to go to femtojoule level energy requirements for synaptic operations. And these available network on chip realizations don't seem to go to that direction, as I will prove in the next slides. Current mainstream asynchronous NoC architectures are quite expensive in terms of area and energy per bit, and they prefer, historically, they prefer to pay this cost in order to get the benefits, and the benefits are an overly high timing robustness. There are actually cost-effective alternatives to these mainstream architectures that are gaining momentum. They are called bundle data architectures, as opposed to quasi-delay sensitive architectures that are mainstream. But these bundle data architectures that are a promising alternative to materialize low power and area overhead, but they introduce moderate timing constraints. And that's an issue for the CAT tools, because it's not straightforward to support these asynchronous timing constraints with mainstream industrial clocked CAT tools. Last but not least, the customization of asynchronous NoC architecture for a neuromorphic environment, in my opinion, is still lagging far behind, because there is actually, the impression is that people are trying to force fit existing NoC architectures into the new application environment. There is not so much customization effort. There is an attempt to reuse things as they are. When we couple this with the poor availability of asynchronous NoCs, because they are not available for the research community at large, they are not easy to design, the key takeaway is that today we have only few design points around. We have only few neuromorphic systems around. Therefore, these are not good days for design space exploration, for customization of architectures for the distinctive features of spiky neural networks to exploit spike-based computation. It's not good time for co-designing your network on chip with your neurocores. It's not, unfortunately, very good time for optimization, because optimization requires the availability of tools, design methods, and methodologies for the community at large. It requires the proliferation of design points, and therefore there is a gap with the current situation. Before going into more details and let you better understand what's going on today in the field of asynchronous networks on chip, and what are the promising solutions that are appearing at the horizon for applicability in the neuromorphic computing domain, I need to introduce some background, couple of background slides on asynchronous design. So any two asynchronous components, such as a sender and a receiver here, communicate via clockless handshaking, and this involves defining a handshaking protocol. There are two common handshaking protocols. The first one is four-phase handshaking, as you can see here. In four-phase handshaking, one transaction implies that the request goes I, the backward propagating acknowledgement goes I, and then the request goes to 0 again, and the acknowledgement goes to 0 again. So you need two round-trip communications per transaction. Therefore, this is not the best signaling protocol for ultra-high performance, because signals have to return to 0 after the transaction. In contrast, in two-phase handshaking, also called transition signaling, each control signal makes a single toggle. So in this case, for the same amount of activity, you have two transactions. The first communication on the rising edges of request and acknowledgement, and the second communication on the falling edges. So two-phase protocols are typically preferred for high-performance circuits, but you need to make your asynchronous logic sensitive to both edges. Therefore, it may lead to more complex hardware. A key challenge addressed by current research is still to employ two-phase shaking extensively in the NoC while retaining low hardware overhead. This is an open challenge. Another essential requirement to build an asynchronous NoC is the data encoding scheme. The most common data encoding schemes are delay-insensitive codes and single-rate bundle data. Delay-insensitive codes, they support robust communication by explicitly encoding both data validity and actual data values. The most common is represented here. The most common delay-insensitive code is a dual-rate encoding, where each bit is encoded with two rails or wires. So bit X is encoded with two wires, and the same thing for bit Y. What's the key benefit of this kind of codes? Actually, independent of transmission time of relative bit skew, the receiver can unambiguously identify when each bit is valid using a completion detector. So this is a very robust data encoding mechanism. So these codes provide great resilience to physical and operating variability. However, as you can see already from this example, most delay-insensitive schemes have poor coding efficiency, 2 wires to code 1 bit, and therefore, also due to the use of completion detectors and the like, they incur high energy per bit due to their wiring overhead as well. So this extreme timing robustness comes with large overhead, poor signaling efficiency, large area, high energy per bit. Alternative data encoding schemes, such as single-rate bundle data, illustrated here, in principle offer higher coding efficiency and lower energy per bit in principle. Because this approach uses a standard synchronous style single-rate data channel with binary data encoding. So we are using a synchronous data channel. The only difference is that an additional request signal, as you can see in this example, is bundled with the data, and it serves as a local strobe at the receiver side when data is sent. And also there is another signal which is bundled, which is an acknowledgement signal, and it is used for the handshaking protocol. This scheme has the advantage of allowing the use of synchronous style computation blocks. However, for correct implementation, it comes with a one-sided relative timing constraint. That's important. And the timing constraint here, which was not there for delay-insensitive codes, is that the request delay, the delay of the request signal, is always longer than the worst-case data transmission. So the request signal must arrive later than the stabilization of the slowest data line. This is called the bundling constraint, and is typically met by inserting a small matched delay on the request signal when needed. So the big challenge here is that currently commercial CAD tools offer poor support for these relative timing constraints. Since commercial CAD tools, they target min-max delay constraints with absolute timing only. You can specify a minimum delay constraint, but with respect to an absolute timing value. While the data path delay to be matched here is known only at the synthesis time. That's an issue. Here there are some useful readings for you on the foundations of asynchronous design, together with the overview papers of the research field and the market trends. They are very instructive readings if you want to to know more about asynchronous design and asynchronous network on chip in particular. So we are now able to understand the current status of the asynchronous NoC deployment and whether current asynchronous NoCs have a match with neuromorphic computing requirements. In fact, in most state-of-the-art asynchronous NoC realizations, designers typically choose communication protocols and data encoding schemes primarily for first-time right and robust design. That is, they aim at simplifying hardware design and at enforcing extreme timing robustness. This makes four-phase handshaking protocols and delay-sensitive data encoding schemes a frequent design choice in this domain. However, these benefits come at a significant penalty in terms of low throughput. Think about a four-phase handshaking protocol, low throughput, high area occupancy, therefore higher vulnerability to faults, poor coding efficiency, and high dynamic energy per bit. Now, let's wonder whether neuromorphic computing is going. And this nice picture highlights the key motivations of researchers to develop neuromorphic computing systems. And this is directly extracted from their paper, work that has been done by Schumann and others in this survey paper on neuromorphic computing systems. And you can see that as we move from the early days of neuromorphic computing to the current days, there is a growing emphasis on low power consumption. So we want to fundamentally go for lower and lower power neuromorphic systems. Other important requirements, in addition to low power, are performance, the need to sustain a real-time performance and high levels of parallelism, and fault tolerance. And then there are other metrics as well. So we have clearly a problem here. We have clearly a problem here because the features of current mainstream asynchronous NoCs are at odds with the growing requirements of neuromorphic computing. Neuromorphic computing is asking for low power, high performance, scalability, fault tolerance, while asynchronous NoCs are typically designed for high robustness, and this comes with an overhead exactly in these fields that are the target for neuromorphic computing. So we have a tension here, and I predict some evolution of the field in order to solve this tension in the near future. Another main issue with asynchronous NoCs is that they currently suffer from limited CAD tool support. And this is fundamentally due to the different nature and optimization requirements of asynchronous timing constraints. For this reason, the onset of bundled data NoCs is only very slow nowadays. Although these bundled data NoCs, they show promise in overall cost metrics, coding efficiency, area, power, and performance. But the problem, I already anticipated that, is that they incorporate bundling constraints, and these are relative timing constraints. And this is a disconnect in the timing models for mainstream industrial CAD tools for a number of reasons. Unlike synchronous timing, these constraints are localized. There is no global timing constraint. Okay? There are only local timing constraints. And unbalanced pipeline stages should be allowed to collectively interact with their own matched local delay. Moreover, fulfilling relative timing constraints is not enough. You need to not to over-design the constraint. Okay? For instance, the request signal shouldn't arrive too late with respect to the data path line to match, because this directly translates into latency and throughput limitations. Another disconnect is that CAD tools, I already talked about this, typically support only absolute minimum delays constraints. But in this case, the data path delay to be matched can be known only at synthesis time. Last but not least, due to the proliferation of local timing constraints in an asynchronous design, the risk is to seriously overload the synthesis engine, thus failing design convergence. These are serious issues. The currently immature timing optimization methodologies and tool flows for bundled data NoCs are currently preventing them from materializing the expected benefits, especially the performance benefits and the area benefits, while for power benefits, we are already there. There are bundled data switches that yield impressive power savings with respect to synchronous counterparts, for example, but they end up degrading performance and area. That's not good news. At the same time, research is typically limited to small-scale systems, switches in the best case, not networks as a whole. And the reason for this is because hierarchical synthesis tool flows are not stable yet. Again, in some rare cases, we have some NoC level works using bundled data, but this work highlight global NoCs that are not able to keep up with the performance expectations. And part of this is due to the immature hierarchical synthesis tool flow. Next, I would like to briefly report on the latest developments on bundled data NoC design in terms of both switch architecture and tool development. This is the outcome of a collaboration between my group at University of Ferrara and Professor Steve Novi's group at Columbia University. So, the network-on-chip switch builds extensively on a baseline asynchronous pipeline, which is a high-performance and low-overhead asynchronous pipeline, which is called Mousetrap, and it has been developed at Columbia University. It uses two-phase protocol and single-rail bundled data encoding. So, as you can see here, we have these pipeline stages, these Mousetrap pipeline stages, and each pipeline stage is simply represented by latch-based registers and simple control logic, a single exclusive NOR gate. So this is a simple pipeline stage with the Mousetrap technology. So you have to imagine that these these latches are normally transparent, and each data item advances through the pipeline elastically based on local conditions. And the way it works is that when the data goes through, it goes through together with its request signal. And the request signal is used to immediately freeze the pipeline stage. And therefore, the latches now memorize the data that has been propagated through them. This request signal is also sent as the backward propagating acknowledgement signal, which allows the previous stage to send different data. When this stage under test is getting the acknowledgement, this acknowledgement signal will make the latch transparent again, and we are ready to store the next incoming data. Therefore, it is a capture and pass protocol. Pipeline stages only close to protect data immediately after it enters a stage. And once data enters the next stage, the current register is actually reopened. So when you build an asynchronous switch architecture on top of this pipeline, what happens? This is the outcome of one such TAMS. So this is a 5x5 switch architecture. And you can see here that you have an input Mousetrap stage and an output Mousetrap stage. In between, you have an input port module that is linked through an intermediate crossbar to an output port module. So the way it works is that you have an incoming fleet together with the request signal, and there are bounding constraints between the fleet and the request signal. And the request signal is used to propagate the acknowledgement backwards for clockless handshaking. Then this fleet, which you consider the head fleet, that is the first word of a packet, this head fleet is immediately propagated to all of the output ports in a speculative broadcast fashion. So it's this head fleet is pushing against all the output ports, but we need to select one. And therefore, in parallel, so there is lots of concurrency in this asynchronous realization, the head fleet will go through routing computation and switch allocation. That is, we will request for access to a specific output port. As a result, sooner or later, this output port will be granted by an asynchronous arbiter. And when the port is granted, the head fleet goes through, and the request signal as well, until it is stored into the output mousetrap stage. At that point, the request is propagated backwards, and it becomes the fast two-phase propagating path for the backward acknowledgement. So propagation here is really fast because it's mainly based on a two-phase handshaking protocol. And once the acknowledgement is received, then the input stage can admit another fleet into the game. So in this architecture, there are bundling constraints. This is no exception. And the following bundling constraints are likely to require synthesis effort to converge. There are actually several subtle timing constraints for functional correctness in that architecture. But for typical gate delay values from industrial technology libraries, these local timing constraints are fulfilled by default. However, there are two bundling constraints that I'm going to highlight now that probably require more synthesis effort to converge. They don't naturally converge like the other constraints that I'm not presenting here. So the first constraint is the bundling constraint throughout the data path. So between any two mousetrap stages, and you can see it here. So you have the data paths, and then you have the associated bundle, the request signal. And the request signal should reach this barrier of latches later than the stabilization of the slowest data line. Similarly, we have a bundling constraint on the routing logic. So you have bundling constraint not only on the data path, but also on the control path. Because, see here, after the routing logic, you have a barrier of AND gates. And the reason for this is that you should not propagate any request to output port arbiters before completing the routing computation. Let me recall you that we are using synchronous style logic. Therefore, these signals here are glitchy, waiting for the stabilization. And so we cannot allow the propagation of these glitchy signals because they would induce in an asynchronous design undesired requests to the output ports. Okay, so the communication from this point to the output port should be hazard-free. And the way to achieve that is to have a matched delay line that makes these filters transparent, but this should happen only after the slowest routing computation signal has stabilized. So we have again a bundling constraint here. So what is the challenge here? The challenge that we have here for the convergence of these relative timing constraints is that the signals to be matched, think about these data path lines, think about the routing computation signals. So these baseline signals whose delay has to be matched, they should be optimized themselves. So we want to synthesize these data path lines and this routing logic for maximum performance. So we need to tune the bundled control signal to an already locally optimized data path or control path delay. And this kind of baseline for the relative timing constraints is known only at synthesis time. While the synthesis is actually taking place, I am actually fixing the value of these baseline data path lines or control path lines, and therefore it's easy to understand that if I want to enforce a relative timing constraints on them, I need to go for an iterative synthesis methodology. And in order to handle this iterative synthesis methodology, we have an entire CAD tool flow in place. It's a CAD tool flow for bundle data synchronous NoCs that makes use of clocked mainstream industrial CAD tools. So it's fully compatible with industrial CAD tools. It's complete in the sense that it covers all the synthesis steps from topology specification here at the top to layout generation here at the bottom, okay? And it goes through logic synthesis for planning, place and route, and especially timing optimization. And the process is fully automated. It aims to achieve the same design flexibility that you have for synchronous design. And this is done for flexible exploration of the design space and not to make use of R macros. In asynchronous design, due to the difficult support with mainstream CAD tools, typically asynchronous switches come in the form of R macros that are inflexible. In this case, the goal is to have the switches as soft macros, the same thing that you have in a synchronous design. Without lack of generality, this tool flow has currently been tested with mainstream CAD tools such as Synopsys Design Compiler for logic synthesis and Synopsys IC Compiler for place and route. And the flow revolves around a detailed timing optimization methodology. That's the cornerstone of this CAD tool flow, the timing optimization methodology. It has been designed with the following goals in mind. Unlike prior approaches, this methodology not only guarantees functional correctness, that is, that the relative timing constraints are met, but also gains tight control over relative timing margins. So it generally prevents the delays on control lines from greatly exceeding the data path delays to be matched, thus avoiding significant latency and cycle time degradations, while at the same time still enforcing reasonable timing margins. Simultaneously, this methodology makes the convergence in satisfying several bundling constraints in parallel computationally affordable without overloading the synthesis engine. In order to achieve these goals, the timing optimization methodology is structured as a nested optimization loop, as hereafter illustrated. So we have an inner optimization loop, which is a baseline iterative synthesis procedure that fine-tunes control path delays associated with locally optimized data path delays. Let's see what it means with an example. So let's say that we have a data path delay and we need to enforce a relative timing constraints on top of it. So we have a request path that has to be delayed with respect to this data path. So the first thing, we run synthesis run, setting a set max delay constraint on this data path, on this baseline data path. And therefore, the outcome is a locally optimized data path delay. Then the methodology automatically extracts the timing of this path and then establishes minimum delay constraints for the later synthesis of the request signal, the bundling signal. So we define the timing margin of X%, and therefore we say that the request path should be delayed with respect to the data path by at least a certain amount. So we enforce a timing margin represented in yellow here. And then we run an iterative synthesis run, and this stops until we have a good matched delay that fulfills the relative timing constraint. In order to gain tight control over the relative timing margin, we also set a maximum delay constraint for the request signal, and this is done at the same time in parallel with the minimum, with the fulfillment of the minimum delay constraint. And we kind of place a wall here in such a way that the request path is not too delayed with respect to the data path delay to be matched. And this is the inner optimization loop, and you can handle several signals in parallel in this way. However, we noticed something. When we have different bundling constraints to be met in parallel, It's true that you can locally optimize them. So at first, you optimize the data path delays to be matched, and they can be different. They can achieve different propagation delays. That's okay. That's the nice feature about asynchronous design. And then you set the relative timing margin and the upper bound on the bundling signal delay. And if you are lucky, then with iterative synthesis, what happens is that the relative timing constraints will be fulfilled. But the problem is that when you try to handle several bundling constraints in parallel, too many bundling constraints in parallel, let's say beyond the 5x5 switch, and for instance, when you go to the topology level, what happens here is that you have several request paths in parallel that have to achieve a normalized target mean delay. And when you run iterative synthesis, what happens is that these request paths never converge, because we are actually overloading the synthesis engine, and it's not able to fulfill all the relative timing constraints in parallel. So in order to deal with this situation, we make available an outer optimization loop that tries to handle the scale and the optimization challenge of complex switches and network topologies. And the basic feature of the outer nested loop is to hit relative timing margins gradually. Let's look at this example. So we have these control signals that have to reach a given minimum delay and not to exceed the upper bound. So what we do is that at first, we don't give immediately the target margin, but we set a less aggressive margin. And we optimize only the signals that are not fulfilling these relaxed minimum delay constraints. So we have two signals that by means of iterative synthesis will meet this relaxed relative timing constraint. Then we shift the relative timing constraint, we make it more aggressive, and we optimize the violating control signals. Maybe this is requiring more iterations, okay, but that's not a problem. In some cases, we also perform an engineering change order. We place manually some buffers on these lines in order to get faster convergence. And finally, we shift the timing margin to the final value until all the control signals fulfill the relative timing constraint. So this is proven to work very nicely across high radix switches and across entire complete network on chip topologies. So let me provide some experimental results that highlight the features, the distinctive features of an asynchronous design with respect to a synchronous one. So we can see here the comparison of the asynchronous switch versus a baseline synchronous one. But since we are running short of time, let me just tell you about this nice feature, because this is unique for asynchronous design, latency. So when it comes to head latency, let's look at the buffered switches that are the most relevant ones. When you look at the head latency, the asynchronous switch is slightly faster than the synchronous one because of asynchronous logic. But when you look at payload latency, so the latency, not of the head fleet, the first fleet of the packet, but of the subsequent payload fleets, you can see that the payload fleets are much faster than the synchronous counterpart. For the synchronous design, there's no difference between head fleet and payload fleet. And the reason is straightforward, because there is a clock cycle and all the operations are fitted to the clock cycle. Therefore, there is no difference between head fleets and payload fleets, while in the asynchronous design, you can exactly tailor the propagation delay of each switch to the timing path that is activated. Therefore, the payload fleets do not go through routing computation. They don't go through switch allocation. Therefore, they just go through crossbar traversal. And therefore, crossbar traversal and link traversal. Therefore, the payload latency is halved with respect to the synchronous counterpart. And that's an interesting property of asynchronous switches that, in my opinion, has not been exploited to a large extent in the neuromorphic computing domain. It's not exploited enough. This asynchronous switch has been compared against a commercial counterpart, an AMD commercial synchronous router in 14 nanometer FinFET technology. This is the first direct comparison of asynchronous and commercial synchronous NoC switches. So the asynchronous NoC was instantiated to reflect the architecture of the commercial synchronous counterpart from AMD, with 2 planes and 2 virtual channels per plane, similarly to what the LoE chip is doing. Although we achieved the post-place and out results, let me now just report post-synthesis results for confidentiality reasons. To be observed that this asynchronous router was implemented with the tool flow of the company. And due to the limited available time, we were not allowed to deeply re-instrument the baseline stable existing flow. So we are implementing an asynchronous switch without, for instance, the outer optimization loop of the synthesis methodology. Only the inner optimization loop is used. But industrial stress tools are used for functional validation. And if you look at the results, these are normalized results in terms of area, latency, idle power, and active power. So it's clear that the asynchronous technology has impressive capabilities to lower area by 55%, latency by 28%, idle power by 88%. That's the most aggressive feature of an asynchronous design, to reduce idle power, to get rid of the idle power of the clock tree, and 58% on active power. That's not bad. And most of these savings are due to the use of single edge-based master registers that has low area overhead, low energy, and critical path latency, due to the lack of a global clock distribution, and due to on-demand activation of the circuitry. But let me present the most interesting results, because today the most frequently used network on chip architectures for neuromorphic systems are QDI networks on chip. So here there is a comparison between the proposed two-phase bundle data switch and the QDI switch. The QDI switch comes from the NoC framework. It's a QDI switch. It's very influential design that has gone through several generations of technology, implementation, and architecture. And here we are considering a high quality recent generation in this table. So the table shows the details. You can look at it with calm afterwards, because there are a number of metrics and a number of comments to make the comparison more precise. But let me report here on the right-hand side the key takeaways. The key takeaways also because here you can see that these networks have been unfortunately prototyped with different manufacturing processes and different voltage thresholds. Therefore, these numbers are not directly comparable. So we tried some normalization of the process node and the voltage threshold, and we report here results after normalization. Normalization process details are reported in this paper. So after normalization, we have a more fair comparison of these values, and you can see that latency is similar. So we are not gaining over the latency of a QDI switch. And the throughput of the bundle data switch is 10% better. And here, we would have expected something better, because the QDI switch is using four-phase handshaking protocol. However, this NoC architecture, this QDI architecture, is extensively optimized because it tried to amortize over time the performance penalty with four-phase communication protocol, through deep pipelining of its completion detection logic and using several optimization features in the synthesis tool flow. So it has been aggressively optimized across generations, and therefore it's able to limit the comparison against two-phase and shaping NoC to 10% better throughput for the latter. But we have significant, remarkable advantages in the remaining metrics after normalization. And in fact, the bundle data router exhibits 72% lower energy per bit and 52% lower area. Okay, so for slightly better performance, we have huge savings for energy per bit and area. And these results clearly correlate to the use of bundle data encoding and two-phase and shaping protocols. It has to be recalled that some of NoC's design space decisions have been made to target extreme robustness, resilience to arbitrary bit skews, to physical operational variabilities, and so on. But some extreme robustness may turn out to be over-designed for many practical system settings, especially if you think about it for neuromorphic computing that exhibits an inherent robustness, an algorithmic inherent robustness to variability, noise, and unreliability. And that's the reason why analog computing circuits have been used in that domain. Okay, so maybe the extreme robustness of QDI is over-designed in this domain. In contrast, the bundle data less conservative style with two-phase signaling, while still including substantial timing margin, leads to major cost benefits. However, in the future, we need more work to explore this robustness cost metrics trade-offs for QDI versus bundle data designs. It's also noteworthy to observe that NoC crossbars, since they are using delaying sensitive codes, so wire intensive codes, these crossbars are significantly more wire intensive, with roughly twice as many wires as for this bundle data realization. However, this bundle data realization here, I forgot to tell you, the name is Tabula. Okay, we finally came up with the name for this. Tabula, due to its less wire-intensive crossbars, is better suited for environments requiring high radix switches, such as irregular topologies, 3D stacking, last but not least, neuromorphic computing. Let me skip this slide and just convey the key takeaway message. I think that there are useful indications that this bundle data technology is promising, both in comparison with the QDI switches and in comparison with alternative state-of-the-art bundle data realization that I'm skipping for lack of time. I refer to the paper for further details. What's next? So all these indicators tell us that it's about time to start customizing this architecture for application to a neuromorphic computing environment, because all the desired properties seem to be there. Let me wrap up this long talk with some considerations about neuromorphic systems and networks on chip for them. So event-driven communication is one of the key enablers that allows the integration of large-scale big brain chips. And event-driven communication is also a very power-efficient way to get system-level composition. However, the current impression that I have is that asynchronous NoC solutions are typically force-fitted into neuromorphic computing system to get something operational, but in my opinion, not optimized. There are ample margins for optimization. So the customization of NoCs for the computational requirements of the biological neurons and the temporal dynamics of spiky neural networks is only limited so far. The question is, are we integrating efficient asynchronous interconnect solutions? Are they helping neuromorphic systems to hit their aggressive low power targets, or are they rowing against? Moreover, we need to enlarge the capability of design space exploration and accessibility of asynchronous NoCs to the wide research community at large. However, I try to demonstrate to you that there are promising new bundled data interconnect technologies that are ready for prime time. The only example of bundled data interconnect technology in a big brain chip is the Intel chip. Although that implementation style is still too much oriented to a synchronous design methodology, and there are more opportunities for lower overhead and lower power by the adoption of mouse substages. Another trend that I envision for the future is a tighter co-design of the network on chip with neurocores for end-to-end solutions. We should be able to emulate more precise axonal delays and exact event timing. And also the exact bandwidth and latency requirements depend on the core organization, on the degree of time division multiplexing which is implemented in neurocores. We need to support the programming through the NoC of synapse cells and to support the on-chip training from the ground up. Moreover, topology analysis for a neuromorphic system is not completed yet, because similar to the brain that has a hierarchical structure, neuromorphic systems have hierarchical structures. They go from cluster, of course, to computing tiles, to computing chips, to arrays of chips. Therefore, we need to come up with multi-level hierarchical modular NoC architectures, and they have to be further investigated for better scalability. Moreover, there is today no consolidated solution for unicast or multicast or broadcast routing. In some cases, you don't have multicast broadcast, you just have unicast. In other cases, you have them, but implemented in software. So here, the trade-offs are not clear yet. Finally, I try to convince you that the routing problem in a broad sense is fundamental for configurable and scalable neuromorphic computing. And the reason is because keeping the connectivity state has a lot of overhead, and therefore having this kind of neuromorphic system fully programmable for arbitrary Spiky neural network is impossible. So how to keep the connectivity state? How to scale to a larger design space of Sparky neural networks? Last but not least, what routing mechanism for the NoC itself? This is typically overlooked in this kind of system so far. Also, I see an emerging trend for hybrid systems that use emerging and silicon-based technologies in a synergistic way to achieve improved accuracy and energy efficiency. However, so far I've seen this limited to the computing part of neuromorphic systems only. In the future, we will think about emerging technology for communications as well. Last but not least, we need to more intensively exploit advanced system integration technologies such as 3D stacking or 2.5D stacking to wire more like the brain. Last but not least, the key takeaway of this presentation is the more we will be able to wire like the brain, the better. Thanks for listening. I know that's a bit late, so if I still have 5 minutes, we can wait a couple of minutes if you want to pose some questions, and then we can close the course. So I will just pause for a couple of minutes and wait for your questions. Thank you. Let me finish the course trying to comment this very nice question that made me smile a little bit. How far are we from mimicking the brain? The answer is obvious. We are very, 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 very far. The numbers that I was reporting before, so picojoule level operations as opposed to femtojoule level operations that we find in nature, it tells you that we are really far away. And even the designers of the most recent big brain chips, they are asking this question, are spiking architecture, are current spiking architectures efficient? The key takeaway is no, they are not efficient, but at least we have a baseline to start working, to start playing with, okay? That's the point. At least today we have baseline to start playing with, and we are using these baselines to make compelling cases, to have some compelling examples that tell us that it's worth working more toward this direction. We have to compute even more like the brain. And the second big gap is that we can't scale to large problems as well, which has been demonstrated in this talk as well. And the reason why we can scale to large problems as well is because we are currently not able to wire like the brain. Okay, so thanks for asking this wrap-up question. Thanks to everybody for attending the course. If you have questions, considerations, if you want to interact with some and collaborate on some specific topics, I'm available. You can reach me by email. Thank you very much, and I wish you a nice summer. Bye-bye.